All right, I must say that I really took the advantage of giving the talk as the last one. Can everybody hear me? Yeah. So because the first three speaker has really set up the stage for me perfectly, I think we understand neural network is an elephant, right? It has all the different pieces. I think the professor Max Welling has talked about invariance, symmetry is important. And Professor Gita has also mentioned that a way to look at it is a rate distortion. How do we code information in a way? And also that Professor Bingyi really pointed out, there's if something at the very foundation of deep networks or something we're doing right, we should also find similar principles from the nature, right? So somehow, my talk is trying to sort of a humble effort trying to put together all the pieces a little bit, including notions such as sparsity and also. And I want to start my talk by asking you to keep two things in mind while you listen to my talk, right? Just like our human brains, we only have data, right? We may have some prior structures, but we have only data to deal with. We don't have models. Our brain does not have any regularizers while they're processing informations, right? And also, by the way, it's debatable, but our brains do not do back propagations. Okay, there is actually a workshop in this New York is trying to ask actually what are all bio-inspired ways of constructing learning process, right? And our brains do not do that, right? So then what other principles or what other things we're doing? So in this case, I'm trying to give a talk on this. Really that since we talk about learning, right? So then let's try to be clear what learning is trying to do. What are the objective? What the learning is trying to optimize? Actually, this is inspired by a discussion with me and with Jan LeCun. He was asking me, we're having this conversation, what the neural network is trying to optimize, basically. Some energy, some quantity, right? This actually draws me back to a work that I did about 10 years ago, 15 years ago, because that's the time when we're looking at learning, particularly clustering and classification. Nowadays, they call it supervised learning or unsupervised learning, about the perspective of compression, right? And that's later on, actually, recently has inspired us to look at this using the compression as the governing principle, the owning principle, right? To derive everything from first principles, that everything we see in the modern days neural networks. So the first idea was justify, we need a little bit of justification for this objective. We call it, instead of compression, there's also, we wanted to learn discriminativeness. That's where the notion of rate reduction comes in. And also we will see that the last piece of our recent work is showing that that's all you need. You only need this single objective. You can derive everything. The structure of the networks, the layers of the networks, the operators of the networks, every single parameters of the network is perfectly derivable from first principles. And also even the convolution structure, you do not impose on your network. You do not choose to use convolution. The data stipulates for it, and we'll see why it arises from there. Right, so let's start with, what do we want to do with learning, right? So we have data, presumably data lies on some very high dimensional spaces with some low dimensional structures, maybe even nonlinear, right? So there actually are three different things, several things, if we delineate the different object. The most basic one is interpolation, right? How data are adjacent to each other, nearest neighbors. We try to interpolate, right? Which data should go together, lying on the same structures. Then the next steps we can ask is that if I have a new data point, a point in the space, tells me which structure or which cluster it may be close to, right? That's related to the classification and so on. And finally, maybe I'm not just to try to save the data, which is very just raw or expensive to store. Can we identify something common, some structural, some representative, right? Make it compact, make it discriminative, so that for other tasks, build memories. So, of course, the deep learning comes along and says, oh, well, we don't care. We just lump everything into the big black box, right? With the deep layers, and we fit the labels. Well, it actually works pretty well, right? That's why we're here discussing about it, why it works, why it is. But there are, of course, problems with it. Everybody knows it, right? That's also another elephant in the room nobody wants to touch, right? Is that if you have a, yes, deep networks, so people know a long time ago, very expressive, right? I can fit even random labels if I choose a very large networks. And then the question is, then if that's the case, then what actually the network has learned? If I just assign random labels to it, anything learned by the network has anything to do with the data itself? Probably not, right? And also that such a network, such a sort of supervised learning, fitting this cross entropy between labels and your data, actually is highly task dependent and not very robust, right? If you have small perturbations to the input, things can fall apart, right? Again, really that, yes, this helps with some practical functions, but this really does not help in terms of interpolating, extrapolating, or interpreting the data. So in the sense that I'm actually trying to change this, everybody talk about interpretation of the deep networks. Actually, I couldn't care less about deep networks. I wanted to know how to interpret the data. I think that's what the question, the main goals are. So now, of course, there are some attempts to try to explain what that deep network is doing. Right? One particular framework was called information bottleneck, using information theory, saying that I'm trying to, really what network is trying to do with all the layers is that intermediately, those features in those intermediate layers is trying to maximize the information correlation with the output Y, and also minimize its information with information X. Basically, this objective is trying to say that we try to extract from X the minimal but most informative feature that correlates with the label, can predict the label, which is associated with the predictability that Professor Bing just mentioned. However, it has a lot of problems, right? Just if you just strive for predictability, you can be very, very brittle, right? It's not stable, it's not very transferable, and so on and so forth. Now, there's actually other big problems with this kind of, theoretical formulation. I mean, this is why, I'll talk briefly about the work 10 years ago. There's a big things in the sense that, yes, you can write down what you want in information theoretical form, right? Just like Gita also mentioned, right? You can write down mutual information, rate distortion, distance between distributions, as if they are at your disposal. Actually, they're not, right? Even computing these quantities, the computation cost could be exponential. And then let alone most of those quantities not well defined if the data has low dimensional structures, right? And also in reality, you don't have the distribution. You only have finite samples, just like our brains do. So what do you do? In this case, can you provide any guarantees of whatever solution you come up with? Right, about 10 years ago, Renee and Shankar, and we were actually looking at this kind of from image segmentation point of view. And how do we learn, right? How from raw data like images, patches, and so on, how the machines can learn structures from it, especially those data has mixed, hybrid, no dimensional structures, right? So one principle we discover is that compression, right? We learn to compress and compress to learn. Turns out that very much is the magic sauce you need in order to deal with all kinds of the caveats I have mentioned earlier. Right. Let's just go very, very quickly before to give you a little bit context of what we're going to lead into in the context of deep networks. Right. So I only have a bunch of points here. I'm not going to talk about this is always started with. We're only going to make assumption about the data. Right. Of course, in classical statistics is that if I wanted to do clustering, I can write down pretend there's a distribution function, and then I try to do the minimize the maximum likelihood of this mixed probability distribution against the mixed distribution. Right, this is called the typical way to solve it, use the EM type of algorithm. Actually, Hinton worked on it back in the 90s. Right? It's wonderful, but the problem is that, again, all the caveats we mentioned earlier, the data, if it's degenerate, finite, you are very, very hard to get this to work. And also it's highly non-convex problems. Then it actually comes to a very basic idea as we did. Is that if the data we assume to have low dimensional structures, and then if we partition them correctly, the data is highly compressible, right? It comes as a very, very basic criteria is that the reason we want to decide we can cluster, we set the data apart as two cluster is because we can save something. Then what do we save? The volume, the storage, the number of bits, right? So this actually comes up with a very, very simple idea is that the reason you classify data is you save something. Now, the only thing boils down to is what is the measure, right? How do you measure the bag of data, right? What's the size, volume, dimension, right? So it turns out there's something very, very interesting that you don't necessarily need a parametric model. The data, if you just take the data as a column of the matrix, right? So we actually derived a quantity called a coding length. If you give me a precision, epsilon is a precision, how much error tolerance you can. Then this quantity, this formula gives you an estimate, very tight upper bound of the number of bits, binary bits you need in order to store the X as a set, or the points as a set, right? You can derive this formula out, from either purely geometric algebraic way, just look at the SVD of the matrix, or from a purely statistical information theoretical way, through sphere packing, or it's related to actually the rate distortion function of a Gaussian source, right, that Gita mentioned. Now, once you have this measure, right, then you can measure the coding length or the volume of any data sets. Now you imagine you just have a scale, right? Then you just, whenever a data set comes in, you try. If you can partition the data in one way, and then the total volume or total coding length is less than put them together as one bag, you partition, right? So basically you cluster to compress, that's it. And of course, this is a gigantic combinatorial problem if you consider all the possible partitions, and turns out that this measure is very tight. You can actually just build up by clustering them in a bottom-up way, right? You only merge two data points or two sets of data points as long as they can save you some binary bits, right? So it turns out this very simple greedy merging algorithm using this quantity, the coding length, works magically, right? It actually finds global minima with extremely robust outliers, and also have to demonstrate the beautiful phase transition behaviors that, and when you change the scale of the quantization, right? Many is not even understood mathematically. I mean, I will point that that's open problems, but yet this pure objective compression alone actually is before deep learning era. It's a state-of-art segmentation. It's all the other segmentation algorithms with tons of heuristics, human knowledges, and also other design filters and all. This is nothing. Just compress the image patches as it is, right? Already gave you the structure of the data. And then that's just grouping data, right? What about extrapolation? If a new data points comes in, I want to decide which cluster it belongs to, right? Of course, the statics, classical statistics is always just to estimate the distribution of each cluster and try to do the map, right? Again, this is issues, right? I mean, the map is not even well defined. Likelihood is not even well defined if the data has low dimensional structures. And also, I only have finite samples and so on and so forth, right? And it's very, very difficult. Although its principle is a great principle, but it's in computationally or in practice, it's actually quite hard to get it to work, right? For real data, for the structures we care about. That's why probably SVM or deep learning will become popular in classification these days. Well, there is a third alternative. We actually can have the best of both worlds. Again, the idea is compression, right? So if I want to assign the data to whichever class it is, maybe the effort for the cluster to interpolate take the extra points in, the cluster will pay extra bits to incorporate that. So whichever cluster pays the incremental of the coding length is smallest, we do that. Right? Meaning that every cluster just try to explain the real data. Whichever one has the simplest explanation wins, right? It's very, very simple. Again, we already have the measure. And it turns out that this very basic coding length, incremental coding length, actually is very principled. When the data size, if you have the luxury to have many, many data points per cluster, then this object function actually converge to the regularized map. But the regularized with one additional term, the dimension of each cluster. And it actually turns out it's a very perfect explanation. Between two clusters, if the map is the same, it will favor the one with the larger dimension. So it kind of has this point of this classification criteria has the tendency to err on the side of caution, right? Very, very, very interesting thing. Now you can do very simple comparison. Using this coding and compression point of view to build a classifier. If you have data, the green and red, right? In the high dimensional space, I actually get a classifier boundary to the left one, right? So you can see this very strong tendency of this object function that extrapolates the low dimensional structures far better than k-nearest neighbor or even SVM with a kernel, right? So at that time, this is about 15 years ago, we did this. We saw those magical behaviors, but we don't understand them very, very well, right? And also we gave up because this actually is very costly, right? In order to build this kind of classifier, you needed to recompute every time against all the cluster with all the data, right? It's non-parametrical, but the principle is correct. Has a lot of interesting characteristic, right? So we stopped there, right? So because our life goes on, deep learning comes around, everybody do superposition, do supervised learning, right? But now the question is, really, that how do we go from such principles that really for long parametric regions, right, data clustering and classification, can we do interpolation? What do we want beyond long parametric model? Well, one thing is that we do want models, right? There are many reasons. I mean, they make things more compact and so on and so forth. If we still make the same assumption, data lies on no dimensional submanifolds, and we do want something normalized or standardized from it. Can we learn some kind of parameterization, undo the complexity in the data? So give me some standard, right? For example, if the data is nonlinear, let's unwrap the linear one, make them linear. Or if the manifolds are close to each other, let's make them apart, right? Discriminative, right? Different subspaces are orthogonal, right? Also, we want the models as compact as possible. That's why we use parameters, right? We use a model structure to identify underlying dimension of the manifolds or subspaces. Now let's be clear. Then what do we want out of this? We start with a very ambitious list, right? Say we can achieve, right? And say we want to learn a map, and if I'm for clustering and classification purposes, we want the maps after mapping. The different classes are very incoherent, right? That's why this is also feature criteria, pattern recognition. We want between class distance large. Within class, we want the distance to be small, but we want to be very careful. We're not talking about the distance, right? We only want the data in which each class to be compressible, right? They're very low, lies on very low dimensional subspaces. And also, we want to capture as many different features per class, as long as those features distinguish themselves from other classes, right? So I don't just want to get that one hot feature. I want to characterize, explain everything, this class of data, different from others, right? So we call it maximally diverse or informative representation, right? Well, this sounds like a very ambitious goal, right? So the question is, do I need 10 heuristics to do this, right? Like everybody does, right? There's a natural measure for all of these properties. There is, right? Let's just recap a little bit. If I have a data, after mapping the Z, I want to put some goodness on how good the Z is, right? So the whole set, I know, expands some space. There's a volume I can measure. The average number of bits, I can encode the location of each of those points. Is given by this rate distortion function, right? Given by the log determinant of this. So this is for all the data sets, the whole data sets, right? Well, the data also, if it's partitioned into k clusters, then I can code each cluster separately because each cluster is low dimensional subspace, it's low dimensional set. The coding length will be much smaller, right? The volume will be much smaller. So hence the average volume, the average coding length will be given by this formula, right? I mean, the coefficient here is just fraction of points belongs to that class. And this is just, again, this fractional points in that class normalized, right? So this is just a way to, this is just, although look complicated, it's just the average coding length for the data partitioned into k class. Then what do we want? The fundamental idea here is I want my data to be orthogonal, to be different classes are spanned as much as possible. I also want each of the class to be compressible as possible. Then naturally, you want to just minimize or maximize the difference, right? The whole set span as big as a balloon, right? So each class is as small as a stick, right? That's the idea, right? So this object alone already builds in all the jargons you heard in the learning, right? Similarity contracts, dissimilarity contrasts, right? And that's why, there's a contractive learning, there's contrastive learning. Well, it's all here. And the question now becomes, let's optimize this, right? We needed to learn a mapping from X to Z such that this quantity is maximized. By the way, by staring at this object function, you see that this function is monotonic in the scale of Z's, the feature Z, right? So in order for, if I have two representations, in order for me to compare the volume, the gain, the volume reduction, I have to normalize the data. Hence the normalization. All the feature needs to be normalized, either on a sphere or the Frobenius norm gets normalized. That's it. As long as the scale is normalized, you can compare things, right? In the literature, right? People do batch norm, layer norm, instance norm, group norm. They're just a manifestation of the same darn thing. You want to compare two different representations. Something needs to be normalized. Then give you intuition what this quantity is doing, right? So if you have data, the left is, let's say you have two data lies on the two lines, two low-dimensional subspaces on the green dots, right? And the right is also on two green dots, but those two lines are closer to each other, right? Obviously, the rate reduction is that the first term is counting all the balls you can pack into the space spanned by the two lines. It's all the blue plus green, right? And then the second term is actually RC. The compressible is associated with only the green balls. Hence, the object is trying to maximize the balls you pack in between. Okay, the blue balls. That's really what you're doing, right? So obviously, from this simple example, you can already see why you prefer, this object function will prefer a solution on the left and the right, right? The right one, those two lines are too close to each other. There's not much two spaces in between. And you can also mathematically show this is true, right? The configuration of the data. Here, we don't talk about statistics, we don't talk about distribution, just the points of the data, right? Reach maximum rate reduction if each class belongs to orthogonal groups. Not only that, the data within each cluster becomes nearly isotropical, right? So this is just added to the, the Aristotle famous said, right? This whole is greater than sum of the parts, right? Here we actually have a different slogan. The whole should be maximally greater than the sum of the parts. That's what we want. And there are actually a lot of people actually trying to do this, similar ideas. I just try to give them credit, right? So people try to do a nuclear norm instead of a log determinant, try to encourage the discriminatives between the classes. Turns out this object function doesn't encourage richness. It actually reach maximum when even each cluster is one-dimensional, which is exactly the phenomena that the Donald-House groups realized, right? The prevalence of neural collapse during the terminal phase. That's associated with the cross-entropy label fading kind of phenomena. And the rate reduction does not have that. We'll see in a second. The second thing I already mentioned this a little bit, right? So really that the rate reduction is a measure of similarity and the contrastness, right? Dissimilarity, right? Whichever word you use it, right? People these days for unsupervised learning or self-supervised learning, basically push, they likely to belong to different clusters should be stay away, right? This is the basis for the so-called contrastive learning, and these days become very hot. The good thing about the MCR, the rate reduction, is that not only measure the practice of contrast learning just to using pairwise points, right? Pairwise samples. This entity actually can contrast triplets, quadruplets, or any number of sets. And you can run some experiments using this as object function to train a neural network. What's the difference, right? Then you can actually monitor now each of this quantity, the rate of this whole set, the compressed set, and each cluster, the average rate of each cluster, and also the difference, right? You can see how the balloon gets blown up. And then you actually compare with the cross entropy and the MCR training on the same data sets, the same layer architecture, everything else is the same except the object function. You can see that the MCR identified for each cluster, the PCA is very rich, right? It gives a 10-dimensional, it spans the whole space, identify all the possible directions that distinguish one class to another. And also another thing is that if you look at the cosine similarity across different class, it's just clean as air, right? It's just push them to orthogonal basis. Then what are those PCA? Can we visualize it? Right. This is on the CIFAR 10 data sets, right? So you remember each class, we actually can identify 10-dimensional subspace, right? We push the feature Z lies on 10-dimensional subspace. Then you can actually visualize what we plot the image along each principal axis. You can see, we didn't tell the machine, right? For machine, they're all birds, but by doing MCR, the machine also discovers subclasses, right? Internal statistics, correlations among each class. And another interesting thing, surprise, is that this framework no longer fit the labels. We use label as side information, right? We only identify subspace that are consistent with most of the data. If the label is mislabeled, say 10%, 20%, 30%, 50% are mislabeled, actually you can see the training, the subspace we get is extremely more robust than if you train with the cross entropy, right? That everybody else do, right? So even just this actually comes as a big surprise, right? So you can see that up to 50% of corruption of labels are randomly assigned. I mean, we're actually 20% higher than the standard neural networks. So this is also, you can do self-supervised learning, right? So in this case, remember our framework is very, very flexible, right? The pi is just basically, it just tells me which samples belongs to the same class. That's it, right? So if I don't have labels, what I can do? Just give me a whole bunch of, this is our entire CIFAR without any labels. What I can do is that, well, I just call each sample as a class, right? I only call, of course, each sample I can rotate, translate, augment, right? I only call those augmented samples as one class. That's it. So every sample set is class of its own. This is a standard setup for self-supervised learning, right? Just invariant to certain class of transformation, augmentation, noise, and so on, right? Again, we use this, just use MCR to this objective to train the network. That's very much the same network, 18-layer, ResNet, and so on. A surprise is that this simple objective, without any heuristics, nothing regularization, nothing, right? Give you a state-of-art unsupervised learning algorithm or across all the different data sets, CIFAR 10, CIFAR 100. The improvement is actually quite significant. By the way, I highly encourage you guys to look at the other methods, right? Each of the other methods usually at least uses 3, 5, even up to 10 different heuristics, right? The last method before us, the DCCM, actually trained again to learn the similarity between pair points. MCR has nothing. One single clean objective function. You optimize, you get the best cluster. By the way, I don't think, given the short of the time, I don't think anywhere near our system is so, optimized, well designed. Done by a couple of students, right? So the last piece of the puzzle, are we happy? No, right? Of course not, right? So this is just saying that, fine, we find a different object function, right? Maybe more intrinsic than cross-label entropy, right? Yes, if I manage to optimize this object function well, the resulting features are indeed more robust and all interpretable because they relies on subspaces, right? Statistically, geometrically, much better, right? Even the dimension, we saw that each principal component gave us something, right? Interpretable. Great, but we borrow the network, right? The ResNet is still a black box. why would they even maximize MCR? It's a mystery, right? How deep, how wide? Also, why do we need a deep architecture anyway? Since we have object function, right? Can we just optimize it? Why do we need, why the deep network helps in a sense? Or bottom line is that then if even I have a deepness architecture, why such linear and nonlinear operators, right? Can we replace the black box network with entirely white box networks? That's the question. In the past, we cannot. Why? Honestly, because the cross entropy, the object function is not intrinsic to the data. Now we do have an objective. We know we are intrinsic to the data. Let's say why networks are necessary. So the idea is very simple, right? Actually inspired by many other previous work is that let's just directly maximize rate reduction with an iterative projected gradient descent. Now, everybody knows what it is, right? So I have object function delta R, which is a function of Z. I just take one step, move those points around, see where those points goes next, so that the rate reduction will be bigger, push those points around a little bit. Of course, because of normalization, we put all the points on the sphere, right? So we don't have to worry about so that's why it's projected gradient descent, ascent, right? Because we're maximizing something. Recall this function looks like this, right? Two terms. Well, first is the total volume. Second is the average volume of all the classes. What are those look like? The first term, very in this simple calculus, right? The first term log determinant goes into is get this interesting identity plus covariance matrix inverse. The second term has exactly the same structure, except just to take the data in each cluster, right? Acting on the data again, and there's a class. So they're put them together. So the gradient looks like some kind of matrix multiply hitting the data, another matrix, sum of the matrix hitting the data with membership. Right? What are those two matrices? Right? I mean, if you have learned statistics well from Professor Bingyu, you should recognize immediately, right? This is exactly the residual from the ridge regression, right? If you're computing using all the data points to explain another point, one point, right? Using all the data points as regressor, do a ridge regression, L2 ridge regression. Then this E multiplied any point is exactly the residual of that. In other words, right? So imagine your whole data set spans an ellipsoid, right? Each point computed at that point is just the residual, how far away that is away from explained by the covariance matrix of the data, right? So now, given the role of this two equation, this two matrix, see the E is positive, right? We want to expand, make the whole volume of data set as big as possible. The second is compression. We want each cluster to be squeezed as possible. So hence, all those residual contribute to that expansion and compression, right? The picture shows that, right? The negative, because it can compress every cluster, expansion is doing that. Right. The picture is very, very simple, very, very intuitive. Nothing, funky. Also, surprisingly, you say, oh, well, I use all the data points to regress any other points, so would it be overfitting? The variation will be too big? Surprisingly, no. Actually, the theory people developed to explain why neural networks do not overfit. Right? This double descent precisely helps here. The regression you compute Q and so are going to be very, very good. The risk actually never grows. Now we have a problem right now, right? So this is just as if I'm moving around the training data, right? I only have the class information for each points on the training data points. Well, yet if I have another test data comes in, I don't have its membership, right? So how can I approximate the gradient at that new point? That's a question. Well, obviously, what do? Approximate. Think about what this pi, the very nature of the unknown is precise the membership of this point to each of the class. Well, you already have the training data. You already know what this CZ is computing. CZ is exactly the residual of this point against each of the cluster. Do a soft mask that assign the points to the nearest cluster. right? Of course, the choice of this is you can have many different ways, but the softmax turns out the one actually works pretty well in this case. By the way, just like you don't need to be precise, right? Here we're not learning the most best classifier yet. We only want something to be good enough so that the gradient is pointing in the right direction, right? Any errors in that, fine, great, congratulations, you are doing stochastic gradient descent, right? So that's adds a little bit of stochasticity to it. So hence, this second term, it becomes nonlinear. Why? Because it has the residual weighted by some gated function, right? Softmax function. That's exactly where the nonlinearity of neural networks comes in, right? Well, if you want, just like any regime that people use these days, right? You can actually just enforce to be the first quadrant. You can approximate actually use an entirely ReLU network. I'll leave the details for you to as exercise. Now, finally put this together, right? So the projected gradient ascent algorithm, they just give you a reiterative scheme, right? Optimize or maximize the rate reduction, right? This is exactly in the form of neural networks, modern neural networks, right? The Z goes in, this identity plus that's the iteration, the L and expansion and the K cluster compression. And then they go through a nonlinear gating scheme, selection or gating scheme, right? And add it up, normalize, go to the next group, right? Take a look at the similarity to ReLU network, residual network, or even later ReNext network, right? People find with more parallel layers, more parallel channels helps. They don't know why, but it does, right? Well, here is a reason, right? So here we did this not try to emulate in ResNet or residual net, ResNet. I think the relationship is the opposite. Is the ResNet and ResNet is actually emulating this process, right? Then you can actually run some just to confirm this network is actually doing the right thing, right? We run on Gaussian, 2 cluster, 3 cluster, 5 cluster. Actually, we run a lot. It's just to show two basic cases, Gaussian. You can see that they will start with the cloud, right? Then push them away and compress each cluster to the follow case, right? Notice that how deep our networks are, 2,000 layers, right? Why? Because we can, right? All the layers are stable. We don't have to worry about any of the numericals. The reason we run 2,000, we want to see that we are not doing any hacks, no early stopping, right? No other tuning. By the way, we didn't learn anything, right? There's no backpropagation. The whole network is constructed forward. There's no backpropagation, no BP, because the forward unrolling is doing the optimization for you. It finds the optimal representation automatically for you. We call it the ReLU network because it's a reduction. What's next? Right? Oh, this is kind of like maybe the vector cases we do clustering, fine. Then Professor Max talked about invariance, right? It's very important for image. We want it to be rotation, invariant rotation, translation. We'll use those two as examples to show this, right? So basically, we wanted that the image after certain rotation, after the mapping, this should be equivalent in the same class, right? Actually, we know, despite all the effort, right? So in fact, the modern CNN is actually pretty bad with, despite other people will tell you, right? Oh, the environment. No, actually it's not, right? The Fourier CNN with the simple recent work study, if you test those carefully, either the fail with very large angle or even small angle where with dense sample, they actually fail, right? Even small deformations and small changes, let alone large ones, right? No network guarantees 360-degree invariance or translation in all places. The question can wait. Right? So now let's take a look at, if we care about points, right? Suppose I have a vector, right? Or shifted version, I should consider them as the same class, right? So this is invariance. Right. Also, this actually defines with this kind of circulant matrix, you define a convolution. The circulant matrix multiply any other vector, give you a circulant convolution. Now, the question is that now for the data points, before I'm clustering, remember I'm pushing one of those points, right? Now I'm pushing their sets. Each sample gets populated with all its shifted version in this circulant matrix, right? That's my raw data now. Now let's compute what the covariance, what the linear operators are. Remember, in order to compute the linear operator, we don't need anything, right? just from the data. Magically, this linear operator E and C becomes convolution. The remains are circular convolution. See, basically it's by virtue of the data, by virtue of your objective, the network become convolution. Nothing you imposed upon, nothing you actually heuristically think will help with invariance, because it's a necessary condition. It's not. And trade-off, but there's actually turns out there'll be a problem, right? Once you shifted the signals around, they span the whole space. If I have a delta function, I shifted everywhere, I can span the whole spaces. So I cannot separate two classes anymore. Here comes a very, very tricky, interesting part. In order to compress, you first lift, right? So you lift, in order to have enough space to compress separate different class, you lift the data into higher dimensional spaces. That's where the multi-channel convolution comes in, right? You lift the function into a higher dimensional space. However, doing linear lifting does not help with separability. You can easily prove, right? If two data points are related by superposition, so is their lifted version, right? Here is where sparsity comes in, right? You cannot, there is a fundamental conflict between shift invariance and separability. In order for different class of signals are separable, you must enforce that each class can only be generated by superposition in a sparse way, right? So with respect to some dictionaries, Z must be sparse. Z cannot be dense. If it's dense, any signal can represent other signals by the shifted version, right? So then what you can do is that in order to get the sparse representation, multi-channel sparse representation, you hit with a lot of analysis filter, which is well developed in the sparse representation literature, then do a sparsified promoting operator. That's a second place where nonlinearity comes in as a necessary condition, not something heuristic. Now, with such multi-channel sparsified multi-channel, there's something wrong with the superscript. Then with the multi-channel signal, sparsified multi-channel responses, then you build your residual network as usual, right? Again, magically, very interestingly, this operator is very, very interesting. It becomes multi-channel convolution in the spatial domain. Okay. Nothing magical. So far, nothing's free. Nothing is for you to tune. Nothing is for you to design. Okay, just from the data. Now, here's another surprise comes around, right? So in order to compute this thing is humongous, right? I left it to multi-channel. There's all circulated version. This is a humongous matrix to do inversion, right? This inverse is very expensive. Actually, not quite. Turns out, those things they are circulated multi-channel data. They actually, after Fourier transform in the spectrum domain, this matrix become block diagonal or diagonal blocks, right? Computing do this inverse is actually, if you do it in the frequency domain, is actually only the cubic in the channel, linear in the number of pixels. So we know if we want to invert general matrix of this size, is cubic in say a cubic in n, right? But because of structure in the spectrum domain, this computation, learning or constructing deep networks is naturally more efficient in spectral domain, not in the original space, right? So we see that in Nature's Explorer, what mathematics dictates, right? Probably in visual cortex, neurons encode and transmit information precisely in frequency. That's why they call the spiking neurons. They don't do in the magnitudes. Maybe this is the reason, right? Here is a pure white box. If you do everything in the frequency domain, do Fourier transform, and you build the deep networks. Nothing here except the learning rate, a couple parameters, the quantization error, everything physically meaningful parameters you get to set. Everything else is completely straightforward by construction, every single parameter, right? So really, if we put the process together, right, we see the necessary role, right? Everything become necessary, not something you tried out, it worked, right? In order to map high dimensional signals between different classes into incoherent subspaces, the nice representation we want, you need first to lift them to explore the sparse structure in each class. Then using the separable sparse structure, you reduce the rate, right? The coding rate. And that turns out precisely unroll itself as the deep networks or deep convolution networks, right? Sparse coding is for separability. Spectral redo networks for shift invariant. That's it. Everything is a necessary condition, right? And we can do something interesting right now. I'm not trying to, we do some baby experiment, right? I couldn't care less. You try to classify 1,000. Let's start from 0 to 1, right? That's the hard part, right? From 1 to 1,000 or to 10,000, that's for the rest of the people, right? So let's just, can we figure out the 0 and 1, right? So here's just take the digits 0 and 1 with 2020 samples. Those numbers can be very, very different, yeah. And then the rotation, we think about each image as a multi-channel signal. Why? We just in the polar coordinates, right? Different R is just a channel, right? The theta is think about the temporal domain as a vector, right? So basically, we just sample the image as a multi-channel vector, convert each image into a multi-channel, one-dimensional multi-channel signal, right? Then the rotation will be a cyclic shift in the theta direction. Then we build a network. There's nothing to learn, nothing to do. And you can see, well, we run 3,500. Well, we can, right? Because it works. So you can see that beginning, these two classes actually are not very separable. This is a cosine similarity between classes, right? After redo, they become orthogonal. You don't have any confusion, right? And this is tested. This is the heat map, right? Between testing and the training, the training and testing after, sorry. This is the before training, this is after training. And here we take 1, 0, 1, 1 from each class. We shift at all possible shifts, every single pixel. We compute their similarity. You can see after the training, there's absolutely no crosstalk at every possible translations, okay? The same with translation in the 2D plane, right? Here we did a little bit of mathematical abstraction. We do actually the 2D because it's cyclic. So we're translating. Imagine the image is painted on the tire. We're translating on the tire anywhere in the world, right? Again, we're not doing just the augmentation. We're not augmenting 5, right? We're not even testing 5 translations. We're testing all translations, right? The image is translated to any possible locations. And we're testing the accuracy, and you get 90%. In fact, again, this is not optimized, far from optimized. Also, we only take 5 channels. Unlike neural networks these days, people take thousands of channels, right? 5 channel works, random channels, by the way. We didn't even design the LS filter that well. So all the experiments, we just use 5 channels. Very, very rough, very, very gross, but it works. It separated the data perfectly. And for all possible rotations, for all possible translations. So that's just to conclude. So you see, there's something very, very simple there, right? You don't need all the fancy, heuristics, inspirations, motivations. Just compress. Learn to compress and compress to learn. It works for clustering, far better than any other algorithm I know. It works for classification, although it's a little cumbersome, right? It's long parametric. It's heavy, but the principle is right. Have even better behavior than SVM or k-nearest neighbor or other kernel method, right? And magically, right, you want to expand the whole data set while you're compressing each cluster. That leads to the rate reduction. That precisely characterizes the kind of configuration you want for your final representation, right? You maximize, sorry, that's a typo there. I just tried to probably copy the minimum max, right? Also, just the simplest way to maximize this object function, right? Gradient scheme needs you construct you a deep networks, right? And there's tons of open problems, right? Even these days, we are recapping, right? For clustering, we see the phase transition behavior. Nobody explained it. Why? Also, we saw the MCR is robust to label corruption. Why? Right? Measure concentration, right? So on and so forth. There are similar results we can inspire us to explain. There's similar phenomena with diction learning, right? Also, here we study the subspaces, Gaussian, mixture Gaussian or degenerate Gaussians, right? So what about the optimal configuration for broader conditions? What if I have more clusters than the dimension and so on? I mean, we actually run experiments that actually give you beautiful crystal-like distributions, but we don't have a theory, right? We don't yet to characterize the optimal conditions of what kind of this. Or what about is a Laplacian distribution or a Cauchy distribution, not the Gaussian? What kind of optimal configuration we get end up with? I don't know, right? Those are the things for, but the principle applies. And also there's a fundamental, we already saw that there's a fundamental trade-off between sparsity or class sparsity versus invariance. This has not been seriously understood, right? I'm not aware of any work related to this now seemingly very fundamental question. And of course, the formulation of MSR is not limited to a supervised setting, right? And we will see, right? We test the supervised or the unsupervised with the self-supervised learning. Right? The pi can be, every sample can be its own class, but there's a lot of room in between, right? How can we join to optimize the representation learning and the clustering? That's for future. Architecture is more to say, right? So far, the Redu network is a multi-channel convolution, but under what condition they become channel-wise separable? Some independence among the filters, ICA, like independent component analysis, and so on. When they make them spatially short, do the motif of each class needs to be short, sparse, right? People have studied those deconvolution problems. New architectures, so far we use gradient descent, right? So now once we understood that the neural network is doing nothing but optimization, then there's tons of tricks from optimization. I can do acceleration, introducing additional skip collections, right? Does it need to do more efficient networks? I'm pretty sure that is the case. Architecture for other, just like Max Welling, Professor Max Welling has talked about, right? Architecture for other groups, invariants. And the magical thing about this rate distortion function is that it lends itself to kernel because the log determinant of this is you can switch ZZ transpose. All you need is the inner product between your data points. You can introduce all kinds of nonlinear kernel into this process, and nobody knows what's going to happen. And also, of course, here we use soft mask, right, to do the gating or whatever, the classify. There's tons of other things you can do, right? You don't have to even to run the L2, right? You can do L1, right? You can update and make the clustering better at each stage of the optimization. Finally, right, some applications. How do we apply to data with other dynamical graphical group structures? Now we have some principles now, right? We know what objective we're looking at, what energy function we want to maximize or minimize. And can we get better transferability or robustness? Now we know if we can identify the low dimensional structures now, all the incoherence, all the principle of uncertainty principles can apply here now, right? Everything we have learned from signal processing, from statistics about robustness can apply here. Right. And also combined with the generative model, so far the whole framework is still very discriminative, right? Can we combine that, kind of identify the structure or distribution helps with the generative model? And also we know, right, nature has neural sparse coding and sparse computing, and both shows up precisely from this framework, right? From duration, right, as a necessary condition, right? Not something, again, you use, right, as a convenience or as something heuristic. Both sparsity and spectral computing are necessary. Right. So those are the few works. So you can see they're separated into two groups. One is what we did about 10 years ago. We're really exploring the clustering classification to address the issue of degeneracy and computability in the high dimensional data. And then really sort of recently that we really realized that really compression is the governing principle that behind deep learning, right? And also maybe learning in general, right? Supervised, unsupervised, self-supervised, contrastive, contractive, whatever, right? You are actually optimized doing the same thing. Also, nice thing is that now we have a very constructive way, like, to create neural networks. At least I think I understand things much better. The roles of those layers, the operators, and so on. So I hope you go home with this slogan, right? I think really that the way to dismiss by or the deep convolution networks are just iterative optimization algorithms, right? In disguise, nothing more, nothing less. Of course, as an optimization algorithm, they can always be improved, modified, and changed, right? Evolved. So that's my talk. Thank you very much. Maybe I have some time for a couple questions.
Hey, there's Ben. Very nice talk. So question is, have you matched the performance using this approach to like very big data? Like, do you have exactly the same performance? I know everything's, nicely Gaussians.
So B, I think the point is that really, should we really care? The answer is yes on the unfair comparison, such as the CFAR. Remember when we're training neural networks with this object function, we know the performance can match. That right now, of course, the white box of the design is still very basic. We still have to scale it up. We don't have that many computers. But I'm pretty confident that this leads to much more principal design network, will be more efficient.
Yeah, one thing is what you believe, one thing is proven, right? So I like the approach, but there's also, the question is also, do you get exactly the same results? I would think that it cannot be identical, and it will be interesting to see and the very big data or some medical imaging data to see the performance.
Yeah, also the goals here is we're testing different property, right? Here we are really giving, you can ask even unrealistically idealistic objective. We wanted to identify this network to be invariant to all rotations, all translations at all possible locations, right? So that's definitely the current network do not even come close to achieve. But of course, here we did this on a much smaller scale. But we showed it actually is doable. There is a principled way of doing it. You know what I mean? Here is a different setting.
No, I don't. I mean, I'm not the enemy. I actually just want to see if somebody who has been really using the data, like say medical imaging, and the performance is also very important. Maybe that's what you do next.
Yeah, exactly. So there's a lot to follow. We just, this is a very still under submission. It's very new work. We just realized in this framework actually lends itself to a very interesting explanation to deep networks and even the new structure of networks, right?
No, I mean, I definitely hope your approach is, but still you need empirical evidence. That's my point.
Yeah. So we did actually the work before. We actually did plenty of empirical evidence on the traditional data sets like CFAR, CFAR 100, and so on. I think we already had enough evidence that this object function is doing the right thing. So it's just a matter of how to find the global optimal, right? So we actually we actually proved that if we use the current network structure, maximize this object function is more than giving you the state of art in terms of robustness, in terms of the classification accuracy, and so on. Right? So whether or not the new architecture will lead to, there's also scalability issues we have to work out. Yeah, that will be definitely for future.
Yeah, well, my experience with a lot of the real data is that the principles are really great, but at some point it's also there's a lot of specifics of things that empirical evidence is also very important. So
yes, of course, yeah. So any other questions?
Giving information theory and statistics class, you should come to give talks to my class in the spring.
Yeah, no problem, anytime.
You're invited.
Okay, good. So any more questions from the?
Do you have also architecture design spin off from this?
Well, this actually has all kinds of implication, as I said, right? So just even that now we know the structure comes from data, from the task, not from something heuristically you try, right? And now that each component is we know the meaning. In the setting, for example, if you're not in a supervised setting, how does it decide those pies, right? The clustering comes in the picture. And there's a tons of implication how the architecture will change. And also, by the way, another thing is that telling anybody, right, that the future deep network needs to be in the frequency domain, okay? Right, we are running Python. The Python does not even support complex numbers, which is a big mistake, I can tell you, right? So if you don't if any forward, backward propagation, you don't support complex computation, you're doomed. I'm pretty sure about that. That will change the architecture.
Push back on that. I like the general like approach from principles, but I also see that there's a lot of interaction with practice. You'll revise your principles too. I don't think complex problems really everything will fall through, but there's a lot of interaction with empirical evidence and domain knowledge that you enrich your principles.
Yeah.
So I think it will have to be a critical process.
Exactly. So yeah, Yellow Kong has also been yelling at you should do things in the kind of frequency domain. Although his point is to still to the traditional neural network implementing convolution, right? Is there some advantages of implementing convolution in the frequency domain? But here is different. Here is that in fact the structure of the network should be naturally in the frequency domain, because that's where you want to you save the computation, even constructing the network, let alone learning it. So that's
you have more faith in general principles. I like general principles, but also I also appreciate empirical evidence. And then I think look forward to seeing with the bigger data.